Jump Game 6, start at the first cell. Each move jumps forward up to k indices. Add every value you land on. Maximize the total when you reach the last index. Example 1, k is 2, so from each cell you may jump 1 or 2 steps forward when in range. Follow 0 to 1, then 1 to 3, then 3 to 5. The sum is 7. Jump Game 6 is score hunting. At index I you only care where you could have jumped from, up to k steps behind you. Take the strongest running total from that window, add the value at I. That step-by-step best total is what we will later call dp. If you rescan that whole window from scratch at every index, you pay order n times k work. When k is big, that hurts. You need the window maximum without touching every cell each time. Store candidate totals in decreasing order. If a fresh score beats older ones in the window, those older entries can never be the maximum again, drop them from the back. That is the monotonic rule. Even the leader eventually falls out of range. We keep a monotonic deque of candidate indices, dp values decrease from front to back, and the front holds the smallest index still in play. If that front index is less than I minus k, it is out of range, pop it and the next candidate moves up. We keep dp as the best score to stand on each index. The deque stores indices only, in decreasing dp order, so the front always has the best predecessor still inside the last k positions. For index 1 we do not scan the window. The deque front is index 0 with dp equal 1. So dp at 1 is nums at 1 plus that best prior, negative 1 plus 1 equals 0. At index 3, index 0 is farther than k steps back. Drop it from the front of the deque before reading the max. That is the sliding window expiration. Now the front is index 1. Add nums at 3 to dp at 1, 4 plus 0 is 4. Before pushing index 3, pop from the back while their dp is less or equal, they can never beat the new entry. The deque becomes just index 3. We repeat for the rest of the array. The last dp entry is 7 for this example. Each index is pushed once and popped at most once from each end, so the whole pass is linear time. Let n be the length of nums, and k the maximum jump length. Time is order n, one scan over indices, and each index enters and leaves the deque at most once, so deque work is amortized constant per step. Space is order n for the dp table and for the deque of indices, which in the worst case can hold up to n indices. Pseudocode for Jump Game 6. Function max result takes nums and k. Let n be the length of nums. If there is only one cell, the answer is nums at 0. Return that value. Allocate a dp array of length n. Initialize dp at 0 to nums at 0. Start a deque with index 0 as the only candidate. Loop I from 1 to n minus 1. While the deque is non-empty and the front index is farther than k steps back. Pop from the front, that predecessor is outside the sliding window. Set dp at I to nums at I plus dp at the deque front, the best prior inside the window. While the deque is non-empty and dp at the back index is less than or equal to dp at I. Pop from the back, those indices can never be optimal later. Push index I onto the deque. Return the last entry of dp.